So today we talk about a classic example of relativity called the twin paradox. In it we'll talk about how it can be shown through the ideas of time dilation that if a pair of twins were born on Earth and one traveled to a distant star at close to the speed of light, when he returned he'd actually be younger than his brother who remained on Earth. So here's how that works out. So we'll be using Ronald C. Lasky's demonstration of this. He wrote an article for Scientific American in which he gave specific values to this paradox. And we really enjoyed these values and thought that they would make it make more sense to you as viewers.
Okay, so we are going to suppose there are two twins, one who travels, named Traveler, and one who stays at home, nicknamed Homie. Supposing at event 1, we have Traveler's rocket ship leaving Earth. This rocket ship can travel at 0.6 times the speed of light. Event 2 is arrival at the star. The star is 6 light years away. Event 3 is arrival back home for the traveler. So because he's traveling at 0.6 times the speed of light, it will appear to the traveler that his journey only takes 4.8 years. We can find this value using the length contraction equation, where L of the traveler equals L of the homie times the square root of 1 minus V over C squared. So, to homie, this trip will take 10 years. This is because the distance is 6.0 light years divided by 0.6 c is the velocity, so we get 10 years for the time.
But for the traveler, since it appears to be 4.8 light years away and he's traveling at 0.6 the speed of light, it'll take 8 years.
Next we'll establish the time spent by the time we reach event 3. So, the traveler will have reached 16 years by the time he returns home, whereas the homie will have measured 20 years on his clock.
Next, we'll talk about each of the perception of the twins. We'll imagine that both of them have a high-powered telescope so they can observe each other's clocks as the traveler travels to the star and the homie sits back at home.
Recall that the traveler will perceive 8 years on his trip, whereas the homie will see it as 10 years. The light will also take 6 years to get back for either of them to see the other. So when the homie sees his brother reach the star, 16 years have passed for him, whereas 8 have passed for his brother.
Looking at his telescope, the clock will be at 8 years, and 16 years will have passed, so time will appear to be at half the speed for his brother.
So for the traveler, the ratio is the same. Since it takes 6 years for the light to reach him at the star, he'll see his brother 6 years ago, or after 4 years have passed. 10 minus 6 equals 4. So, taking 4 divided by 8, the amount of time that passed for him, it'll appear that time is passing half as quickly for his brother. Now we'll observe what would happen if the homie were to watch his brother coming home. So, 16 years will have passed by the time he gets home. But for the homie, only 4 years will have passed since he left the star, since 20 minus 16 equals 4. He will watch 8 years pass on his brother's clock, while 4 years will pass for him. Therefore, it'll look like his brother's time is going twice as fast as his. Again, as the homie watches the traveler, 4 years pass for the homie, and 8 years for the traveler.
Time appears to be going 2 times as quickly.
A similar effect applies for the traveler. Recall that he saw the homie after 4 years had passed in the homie's time when he had reached the star. During his ride home, the homie goes from 4 years to 20 years.
So on an 8-year trip for the traveler, 16 years pass on the clock of the homie, and boom.
Time appears to be going twice as fast for his brother.
Upon arrival, the two twins begin to compare their clocks. The traveler's clock appears to have 16 years elapsed on it, while the homie has 20.
Supposing he left at age 20, the traveler will now be 36, whereas his twin will be 40.
Now you know!